Hi, and welcome back to the channel. Today we dive into Delta Lake's schema management capabilities, a crucial aspect of maintaining data quality from your data lake. Now, this just isn't about preventing bad data. It's also about making your data reliable, consistent, and in some use cases, flexible to source changes. The prerequisite here is the Databricks Delta Lake high-level introduction video, link in the top right-hand corner. So make sure you understand these basics before proceeding. So let's lay out the objectives. We'll start off by defining Delta Lake's Schema Enforcement and Schema Evolution features, as well as give a few data quality scenarios that you could use it for. We'll look under the hood to really understand how it works. Then a data architect's view of when to use enforcement versus evolution for your medallion architecture data flow. Next, we'll get hands-on and run a sample Py script to see schema management in action. Finally, I'll give a short summary of what we've learned and wrap up with some final thoughts on what we need to think about in regards to schema management and data quality strategy. Now, the schema enforcement part is something you're probably familiar with on other database platforms, also known as schema validation. It's the process of ensuring data is being written to a Delta Lake table and that it conforms to the table's defined schema. So no schema change is allowed unless you make an affirmative choice to change it. This is default behavior. You define the schema in PySpark using struct type and struct field from PySpark.SQL.types, which we will use later in the Databricks demo, so don't have to worry about that now. If you violate the schema rules, Delta Lake will reject the right operation and throw an error. This enforcement prevents bad data from polluting your data lake, ensuring that your data remains consistent and reliable. Delta Lake also enforces data quality by supporting two types of field or column constraints, which perform value level checks, not null and check. These work alongside schema enforcement, which is a separate mechanism for schema level validation. Again, we'll show this in the PySpark demo a bit later on. The concept of schema evolution, on the other hand, is the ability of a Delta Lake table to automatically adapt to changes in the data being written to it. This is particularly useful when dealing with evolving data sources where the structure of the data may change over time, for example, allowing you to ingest data without having to manually update the table schema every time the schema changes. Configuration-wise, schema evolution is activated by adding the merge schema equals true to your .write command on a case-by-case basis. This is the recommended approach because it provides precise control over which data operations can automatically or tables automatically evolve the schema. You can define a global approach using spark.databricks.delta.schema.auto merge option, but this is less common. However, it can be useful in development or testing environments where broad automatic schema handling is desired. So as an example, if a new column is added to a data source, schema evolution can automatically add that column to the Delta Lake table. An important caveat here is that schema evolution does not allow you to make every type of change imaginable to a particular column or table. Allowed changes, as discussed in the previous example, is adding a new column. This is probably the most common example. Also adding new nested fields. So if you have a struct type column, new fields can be added to it. Also upcasting data types. So changing a type, but just to a wider version of itself. For example, a short type to an integer type. More edge cases that are allowed are null type promotion. So, for example, you ingest 1,000 rows of data, and but this specific column is entirely empty. Spark infers this as a null type. Then suddenly you get one more row and it's a string. So Delta is smart enough to promote that column from null type to a string. Another edge case is merging unrelated schemas. So as an example, you have a table with columns A and B, and you append a data frame with columns C and D. The new schema becomes A, B, C, D. Danger is with this, having this kind of approach is confusing for analysts and can degrade performance if not managed properly. Now, the not allowed list is that you need to use overwrite schema option. So, for example, drop column or rename column. Now, those two, you can enable column mapping in the table properties, which allows you to do this. It's as a metadata operation without a full rewrite. But by default, even if you have that merge schema equals true, you won't be able to drop a column or rename a column. Also, true data type changes like a string to an integer, for example, you'll need that overwrite schema option. So now that we've looked at schema enforcement and schema evolution, the sort of two features of schema management, let's look at a few more use cases to understand how these features can be applied. So firstly, an example of enforcement is just basic data ingestion from multiple sources. So when ingesting data from various sources, each source might have a slightly different schema. And that's where schema enforcement comes in. So that only the data that conforms to that unified schema is actually written to the Delta Lake. On the schema evolution side, it's all about data preservation and not disrupting your pipeline. So as mentioned earlier, data sources can evolve over time. New columns may be added or a wider version of a data type might be implemented, and that's where schema evolution comes in. It allows you to seamlessly adapt to these changes without disrupting your data flow. In regards to data quality control by schema enforcement, it's really a really critical component by ensuring only valid data is written to the Delta Lake table. And this prevents data corruption and maintains integrity of your data. Also on the enforcement side is preventing data dilution. So this can occur when new columns are appended so frequently by schema evolution that a formerly rich, concise table loses its meaning and usefulness due to the data deluge. So, a point for enforcement, but also a cautionary tale about too much of that data evolution. Finally, auditing and compliance, which covers both enforcement and evolution. Schema management can be used for auditing and compliance purposes by tracking schema changes over time. And you can maintain a history of how the data has evolved and ensure that it meets regulatory requirements, for example. So with that auditing and compliance use case and tracking schema changes, let's look at the mechanics of how schema management works under the hood. Delta Lake uses the transaction log in that _delta_log folder to manage schema information along with other metadata about the table. So when you write data to a Delta Lake table, Delta Lake checks the schema of the data against the schema stored in the transaction log. If enforcement is enabled, Delta Lake will reject the write operation if the schema doesn't match. But if Schema Evolution is enabled and the schema change is approved for evolution, Delta Lake will automatically update the schema in the transaction log to accommodate the new data. So the transaction log ensures that all schema changes are atomic and durable. See the ACID transactions video in the link above regarding atomic and durable. This means that the schema changes are either fully applied, so that's the atomic part, or not, even in the event of a system failure. So from an architecture perspective, let's look at how you might implement schema enforcement or evolution in your ETL pipeline or medallion architecture. We won't discuss medallion architecture here, but in layman's terms, bronze, silver, gold is roughly an extract, transform, load kind of equivalent. We'll probably have another video on that at some stage. So in regards to bronze, so that in ETL, that's really the raw truth. It's got a raw truth philosophy. So the goal of a bronze table is to be a faithful reproduction of the source system. It's your safety net. So schema inference is usually enough here. If the source system or like an API or a NoSQL database adds a field, you generally want your bronze table to just absorb it without failing. There is a risk of having struct types, the struct type in bronze, so defining everything. If you define a strict struct type in that bronze ingestion and the source system changes, like a new field is added, well, your source and ingestion pipeline might not map. The compromise, most architects use Schema Evolution, depending, and we'll get into the depending part. So using that merge schema is equal to true in bronze. This allows the table to grow automatically as the schema or as the source evolves. Sometimes the source is evolving at the same time as you're trying to build it out. And this ensures that you never lose data because of a strictness error, strictness philosophy. Now with silver and gold, so it's like really the refined quality stage. Silver is where the data quality theme truly begins. It's where you filter, where you clean, and where you join data. Here predictability is king. Downstream consumers, expect like a Power BI or machine learning models, expect silver and gold tables to be rock solid. If a column suddenly changes type here, it can break, the business, not just the pipeline. So, by using a struct type in the silver layer, you're creating it like a contract. You're saying that I don't care how messy bronze data was, the data in this table is, strictly following these rules. Okay, so, but when should you use struct type in bronze? There are certain scenarios or circumstances where you might use it. One is file formats without any metadata. So if you're reading CSVs, you almost always need a struct type in bronze. Without it, Spark has to read the entire file twice to guess the types, which is slow and often gets the types wrong. Interpreting a zip code, for example, as an integer, or dropping leading zeros. Also sensitive data. So if you need to ensure that specific columns like social security numbers are handled as strings and never cast to numbers. Your struct type provides that security at the point of entry. Also, they're a situation where you might have strict compliance if you're in a highly regulated industry like banking or healthcare, where you're legally allowed not to store unexpected data fields. You would use a struct type in bronze in this circumstance to act as a hard filter. I will mention that with the silver layer, of course, you can implement your DDLs and your constraints, your field constraints, and your business logic at the silver layer. Always it can be a good idea, definitely, but it depends on your data and depends on the requirements. Probably in the demo, I'll be looking at bronze and silver, and I'll use a SQL DDL for silver just to demonstrate the differences between using data frames and the DDL. Okay, so time for a demonstration in the Databricks tool. So we will be using Databricks Free Edition as per previous videos. Firstly, doing a bit of a setup of the initial bronze ingestion and an example of Schema Evolution. So establishing that landing zone that can change. Then we'll look at an example of null promotion, another example of Schema Evolution. Then moving on to silver ingestion, applying strict data quality. So this is where Schema Enforcement will come in, using a SQL DDL and check constraints. Finally, we'll have a look at the overwrite schema functionality. So it's the ultimate reset button for your schema. Okay, so let's jump in. I've got Databricks Free Edition up and running, and I've got a notebook called Schema Management Notebook with all the various scripts that we need for the demo. So why don't I just kick things off? I've got a cleanup script first because I've run this a number of times, and you never know your luck. Might have something lurking somewhere, but let's say I just run everything. So run all below. Okay, so this one's just the two tables that I create here are the bronze events and the silver events tables. So I'm just dropping those. Next is a bit of a setup and also creating that bronze events table. So what we're doing here is we've got a row of data, user one, login, and the date timestamp, all set to strings. This is the structure here using struct type and struct field for the data frame. So it does need to be defined here for the data frame. It needs to know that there's 3 columns at least, and then we just create the data frame from the data and that schema. And this is the important bit. We've got evolution enabled, so the option of merge schema equals true, and we're just appending this to it and creating a delta table called bronze events, and it's a managed table because we need to use managed tables in this free edition. So just basic printing it out, looking at the schema here, 3 columns, user ID, action, and timestamp, all strings, and there's that one row of data. So pretty easy stuff. Next is a little bit more involved. It's example of schema evolution. So null promotion. So as you recall, there could be a column added in the source, and it's got no data at the moment. It could be a placeholder, or the data hasn't arrived yet, and so it's brought into Databricks into the into bronze, and yeah, what it'll do is it'll set it as a null type. So it doesn't know what the type is; it's not defined. So it'll just put it as a null type. Here the example is the only row of data it's got is this one. It's adding this action details column, and this is mimicking basically the source, and action underscore details is set to none, and that's it's defining that null type or void type. We create a data frame out of that, the data in the schema, and then we append that data to the bronze events table, and using that merge schema equals true. And then we've got a brand new schema there, which we'll show down below. But then the last bit, the most important bit, is it transforms from void or null to a string. So another row of data comes in, and with an action of purchase. The first one was login, then the next one was log out, and this one's purchase. And you can see here, instead of none, which we had down below, none, we got test. So, and test is obviously a string. So when it saves the data or appends that data, it'll actually change the data type from a void data type to a string. So then I've just got a bunch of print statements and reading tables just to show you. So first one is, then we define the struct type and the struct field, and there's that action details, which is void. Okay, and then we promote that. And I'll just scroll down a little bit further, and then we promote that by just inserting the data. And it's smart enough here on the test. This is inserted, and you can see here action details is miraculously changed into a string data type. So it can be pretty useful, especially when you're dealing with a source that's always changing or getting added without maybe placeholders, and you're trying to build out the medallion architecture or the ETL at the same time. Next, I've run this all, of course. There's the silver ingestion, and that's really it should be your schema enforcement. So this is all about schema enforcement. So notice that we're using SQL DDL here instead of PySpark data frames in our bronze ingestion. There are a number of advantages to doing this. One big reason is that bronze is more about flexibility, just getting the data in, being more adaptive to changes, where silver is more authoritative. It's all about governance and not, getting unexpected junk tables, populating silver. There's also the server-side enforcement. So the SQL advantage is the constraints like not null and check are stored in that Delta Lake transaction log. Now, PySpark is great for enforcing data types. So it must be an integer, for example, but it's pretty terrible at enforcing business logic. For example, like the price is greater than 0, for example. It's much better to use altered table add constraint, which we'll look at further on. But it really is a philosophical mind shift here from bronze, being more flexible, and schema on right, which is the governance, the silver layer. So having rules defined, so we've got creating a table and very defining the structure, string and timestamp. This time, instead of in bronze events it was a string, but it's a timestamp, proper timestamp this time. So yeah, it's pretty straightforward stuff for DDL. Then we're, as discussed previously, we talked about table constraints or field constraints. So that's that business logic, and we've just added one here that we've put a constraint on the action. So action can only include the data that we've already got. So we had got login, log out, and purchase. So I can scroll down a little bit more. So we just, to show you, I'm using the describe detail function. And if I go down here, hopefully, here we go. So there's just a little part here where it's valid actions. And you can see here, it's constrained on login, log out, and purchase. So it should be a fairly simple way of testing that enforcement and crashing it, basically. So first things first, we kind of mimic some kind of source to add that to it. So we've got, we've just defined it here as a silver temp. And then what we're doing is we're going to put the action as hacker temp, not log in, log out, and preserve. So that should fail. So we're adding that bad action data, and we're using that silver temp schema. And then when we write it, we should get this rejected by Delta Lake check constraints when we do our append. Also, we had a not null on the DDL. Yeah, the login was a not null, or the ID was a not null, sorry. Yeah, let me just double check. What was it? The user ID. Here we go. User ID was not null. I lost my train of thought there. Okay, so here we're defining or just putting none as the user ID. And so this will be bad data and it should fail because it's got that rule saying not null. Then we're just writing a try catch exception, and we should get a rejection by Delta Lake not null. So if we scroll down here, we just got those two events, invalid action. So that was when we had that schema mismatch. So we brought in that hack underscore attempt for the action here, and it wasn't in the list, so it's going to fail. And then we've got just checking the not null constraint, and that's working. Tried to pass a null in it, and it didn't like it. Last but not least is the ultimate reset button. It's just overwrite schema. So just having a new table, new schema here, just with two columns to demonstrate a user ID and an action. And then we just put in one row of data and using that schema there. And then we're just printing out the results. And what we're going to do is we're going to use that data frame and overwrite silver events. So then it should turn into just two columns. So before that, we had 3 columns in silver. We had that timestamp, and after the overwrite, we had user ID and action. So yeah, so pretty straightforward for the enforcement. Should be relatively familiar with enforcement, but yeah, it's really good to know that evolution as well and how that ties in. Okay, to sum up and recap, silver enforcement essentially is your shield. It's the default setting, and it protects your silver and gold tables from schema drift. It rejects data that doesn't match your predefined structure, essentially. Schema evolution, on the other hand, is your flexibility. By using that merge schema option equals true, for most cases, you allow your Delta Lake to adapt. It's perfect for bronze tables where the raw truth might change. Constraints, which you're probably all familiar with, are your guardrails. Structure is just the start, but using field constraints and not now rules ensure the values inside your columns actually make sense for your business logic. In the next video, we'll take on performance in the Delta Lake. In data quality speak, that's timeliness. So stay tuned for that.